I'm a graduate student in Northeastern University, majoring in computer science.
Background revolves around like data engineering and pipelines. This past summer, I worked for a mutual fund company in Chicago, where I worked with a partner on an intern project where we built a data pipeline.
At UCLA right now. And I would say from my prior experience, I've worked a lot with both data mining, as well as using machine learning models to integrate that data into something that's more applicable to users.
So let's imagine you're given a list of relationships between individuals in a family, and you'll be given a list of pairs as input, where the first individual is the parent and the second individual is a child. So I want you to write a function that takes in this list of parent-child pairs as input, and I want you to return two collections. The first one containing the individuals with 0 parents, and the second one containing the individuals with exactly 1 parent. So if you look on line below line 26, you'll see for the output of the function you're going to write, find nodes with 0 and 1 parents, and you're given the pairs as input. So you see the first collection has individuals 1, 2, 4, 15, and 30, because if you look on the graph on line 6, you see that each of those individuals have 0 parents, so we add them to one collection. And then the second collection has individuals 5, 7, 9, and 16, because again, if you look on the graph, you see that each of those individuals have exactly 1 parent, so we add them to a separate collection.
Okay, so I just traverse the pairs array, and then for each pair, I will first I will have a hash map to store. The key will be child, and the value will be its parents, and it will be a list of the child's parents. So I will traverse the pairs, and then for each pair, I will put the child and the parents into my hash map. And after I traverse the pairs array, I will traverse my hash map and see and put those child and those child who has only 1 parent, put them into my second answer array. That's my
Yep, that sounds like a good approach. So you can get started when you're ready.
Oh, okay. So So it will.
So what's the time complexity of your solution? And if you look on line 33, you see where we define n. What's the time complexity?
The time complexity will be O(n), because for line 44 to line 46, I traverse the input array once, and for line 48 to line 52, I traverse the hash map once. The size, the size will be no more than
And
O(n).
the space complexity?
Space complexity will be O(n), because there are like totally n items. I store them in the hash map, and no more than n items in the answer array.
Okay, so thanks for going through that.
So now so my intuition for now is I don't think I'm going to write any sort of tree structure. I think I'm leaning towards like writing a hash map, maintain a set of every like value that I've ever visited, and build up a hash map where its key would be a parent, and then children would be the values, and then I compare the keys to the set list. If a key is not, if something is in the set and is not the key, it would have no parents, and then I could just step through the map and check. Okay, all individuals exactly 1 known parent. Huh. Okay. Well, yeah. Okay. My solution would not be too good at that. Saying all individuals exactly 1 known parent. Okay. Well, to start, I think then I'll maintain 2 hash maps. One where it's parents map to children, and one where children map to parents, because the first one I would need parents mapping to children, and the second one I would need children mapping to parents.
Okay.
Okay. Yeah, and it looks like my input matches.
So what's the time complexity solution? And if you look on line 33, you see where we define n.
Okay, number of pairs in the output. So this is order of, sorry, I'm gonna write comments. So this is order of n because we're stepping through every single pair. And then this is also on the order n because the worst case scenario, every element in every pair is unique. So we would have to step through 2n elements basically, which is still order n, and then so the entire complexity is order 2n, which is also order n.
Okay, and space complexity?
Okay. Space complexity. So I'm maintaining the child keys, which is okay. Maps basically every child that I visited to the number of parents they have. Okay, well, first I know that the visited set is similarly O of n for the same reason as down here. And then child keys, I'm tempted to say it's O of n, but I want to think about it a little bit. So number of pairs, space O of n. And then for every child, yeah, I would also call it space O of n. So the entire space is also O of n.
Okay, so thanks for going through that.
Got it.
Okay.
I'm just going to take some time to read the problem more specifically.
Yeah.
So the data is formatted as the list of parents going to children,
Mhm.
right?
Yeah.
And each individual is assigned a unique positive integer identifier.
Mhm.
So for this first stage of the problem, we're trying to, let's see, so we return two collections, one containing all individuals with 0 parents, one containing all individuals with exactly 1 known parent. Okay. And the way I'm going to be working with this problem is I'm going to set up a dictionary.
Okay.
And I'm going to be iterating through all the pairs, and for each parent-child relationship, I'll make a key that is the value of the child. We can do this because we know that each particular individual has a unique positive value, and I'll set that particular key to +1 of its current value, where all of the children start at 0 initially.
Okay.
And then after we initialize this dictionary, after we go through all of our inputted pairs, I'm going to look at all of the particular keys in this dictionary, and if the parent value is 0 or 1, we know to append it into our 0 parents collection or 1 parents collection.
Okay. Yep.
So I
Sounds like
can begin
everything.
here.
So you can get started when you're ready.
Here we go.
Yep, that was it. So what's the time complexity solution? And if you look on line 33, you see where to find n.
Sorry, could you repeat that? You cut out right there.
Can you describe the time complexity of a solution? And if you look on line 33, you see where we define n.
Okay, so n is the number of pairs. So breaking this down, we first have O of n here when we iterate through each of our different pairs. And for our child and each of our individuals, this is O of n as well for our iteration. And we know that to add to a set as well as the dictionary, Python treats sets and dictionaries sort of as both hash maps. So those both take O of 1 time. And as such, the total amount of time for this operation would take O of 2n, which would reduce down to O of n.
Okay, and the space complexity?
In terms of the space complexity, let's see. The space complexity would be O of n as well, because we can see through our storage that we're adding n elements total because we have n different pairs.
Okay, so thanks for going through this. And now we can jump to the next one. So this time, I want you to write a function that takes in the pairs and 2 of the individuals from our data set as inputs. And I want you to return true if the 2 individuals share at least one common ancestor. So if you look on line 28, for the third test case, given 6 and 8 as inputs, we return true, because if you look on line 14, you see that 6 has ancestors 3, 5, 1, 2, 4, and 14, and 8 has ancestors 4 and 14. So because they do share a common ancestor, we return true. So again, you can take some time and read through the problem some more, then you can let me know your approach, and then you can get started coded.
Okay. Okay. So I think I can reuse some code of my first problem. Yeah. Since I have constructed the hash map, and then I just get the ancestors of the given two nodes and see and compare their parents array. If they have like common parents, I will return true. Otherwise, I return false.
How do you determine if they have a common ancestor?
I think I can use I can like convert the ancestors list to a set and see whether the 2 sets have like intersection.
But how do you get all the ancestors?
All the ancestors.
Yes.
Oh yes. All the ancestors. Oh, okay. So I still need to. Okay, so I first need to do BFS or DFS to get all the ancestors of this node, and then I can compare the 2 ancestors set.
That sounds like a good approach. So you can get started when you're ready.
Okay.
Yep,
was
that was
true,
good.
true, true.
So
was
what's
true.
the time complexity resolution?
So the time complexity will be ON because for the constructing the hash map is ON like in the first question, and then for both nodes I search for all of their ancestors. It takes ON because I will traverse like no more than all the nodes.
Okay, and the space
So-
complexity?
Space complexity is ON.
Yep, so thanks for that. So now,
Okay, and should I erase what I have written for the previous problem?
it doesn't matter. It's up to you.
Okay, I think I'll just erase it just to keep it out of the way. Okay. So this time, okay, I'm also inclined to make a hash map again that maps children to parents this time because we want to check if there's overlap. We would be wanting to check for the two inputs whether there's overlap between the parent list of two children. So like say it's as you said like 8 and 6. I would work my way up the tree and establish what each higher level ancestor is. So like parent or like grandparent.
How do you find
So
it?
like well, I would want to take in all of the inputs
Mhm.
and assemble a I would want to assemble a map that ooh. So also quickly in this example, the parents of 8 would only be 4 and 14, correct?
The ancestors, yeah.
The ancestors, okay, sure. So just to work through this base case. So there's a pair here 4, 8. I would map 8 to 4, but then so it looks like I would need to pass through the hash map twice. Once to assemble all of the direct ancestors, because my problem is, so 8 would map to 4, but we also want 8 to map to 4's children. And if there was even more down the line, we would want, we would want 8 to also map to 4's parent. Okay, I think actually I'm gonna run with the hash map of just the direct parent every single time. Assemble a list of every direct parent I visited. I think it would also be helpful for me to start coding a little and then kind of see where it goes, if that's okay.
Okay, yep.
Okay.
Yep, that's good. So what's the time complexity solution? And if you look on line 38, you see what we define n.
Okay, number of pairs in the input. This one is more complicated than the last one. Well, here I'm assembling the map, so this is order of n. Step through every single pair.
We'll say for the purpose of this problem, they'll have at most 2 parents.
Okay. So essentially, for each of these, so yeah, these 2 stages will have the same complexity because usually this one will finish first, but worst case scenario, it'll run through both entire branches and there are no intersections. So what would be the number of branches given a node? Worst case, you start at one of the bottom leaf nodes and work your way up. The number of pairs would be the number of relationships. So the number of like edges, I would call them in this like pseudo graph or tree. Okay, I'm gonna call this ordered log n. I'm gonna call both of these ordered log n because since every child can have at most 2 edges coming vertically from it as parents, that means we'll reach the top of the tree in worst case scenario log n of time. So total complexity would be order log n plus order n, and n trumps log n, so it would just be order n.
Yes, so the time complexity is of n.
Yes.
And space complexity?
Okay. A similar process, I would call this space O of n since we're storing every single pair. Yeah, we're essentially restoring every single pair relationship, but in a more like collective matter. And with this one might be a bit more tough. So branches only ever has one. What do I maintain? So I maintain n1 ancestors and branches. So the space of, actually I'm gonna do the branches one afterwards. This one, we start with the space of n1 ancestors. Worst case scenario. Okay, yeah. Well, worst case scenario, we have to maintain the entire tree as the ancestor. So say like this entire, starting with 8 and 5, everything here is cut off, and 11 would be like our leaf node. If we're looking at the ancestors of 11, we would have to store the entire tree, which would be order of n space again. I'm sorry, that's the wrong one. And then, so for any one level of the tree, so essentially, what's the widest any one level can be in this structure? Okay, I'm just going to draw this out for a second and give it a little thought.
Also, just as a heads up, because we do have another problem, I don't want you to spend too much time on this.
Okay. Yeah, I'm not too sure about this one. I'll just give it log n, because I'm not sure. I know log n should be the height, but I'm unsure what the width of a tree like this would take up in space. And then the ones on the bottom would run exactly the same. So you'd have space O of n, space log n, O of n again. So 2 times log n plus n for all these branches down here, and then plus that at the end. So total complexity would be 2n plus 2 log, so 3n plus 2 log n, which would simplify down to n again.
Okay, so thanks for going through that.
Okay, so a clarification. Let's look at 1 and 3, for instance. We return false because they need to share a common ancestor, and the particular individual itself cannot be considered an ancestor, correct?
Yeah, that's right.
What I'm thinking right now is that this is a problem where we'll have to perform a breadth first search. That's my current idea right now, where we'll have to look and see if we can reach one other. I have one question about this interview, actually. So do we prefer a correct answer more so than getting the optimal result?
Yeah.
So an idea I have is this. Let's first construct this parent-child relationship as we established prior. But for now, let's instead work with a breadth first search, where for every node, we see if it's a possible ancestor. And for every node, we continue down a breadth first search. And if we're able to find both particular nodes in this breadth first search, then we know that both of these nodes have a common ancestor. That common ancestor would be that particular node we're doing the breadth first search from.
Okay. But how exactly do you get the common ancestor for 2 individuals?
So my idea is as follows. We can scan through every node in our graph here, and we can look at all of its neighbors and recursively keep on searching.
Keep on searching what exactly?
Keep on searching through all of the childs. So for instance, let's say that we start at node 14, we look through its children, we would go to 4, then we would go to 5, 8, 9. When we see 5, we mark that we've seen 5. And let's say that we're trying to find the pairs 5 and 6, for instance.
Okay.
And from 5, we go to 6 and 7. When we see that 6 has been found, when we recursively search, we also mark 5 previously. Since 5 and 6 have both been found, we know that we can return true that there is a common ancestor.
Yep, that sounds like a good approach. So you can get started when you're ready. Yeah, that was good. So what's the time complexity solution? And if you look on line 38, you see where we find n.
Right, so the first step is building the adjacency list. So we take O of n as we are iterating over n pairs. This is where the program really isn't too optimized, but regarding the time complexity, we have O of n for each of our individuals. And for our depth first search, worst case, depth first search here, let's see. In our worst case, it would be possible to iterate over all nodes. Because if we imagine our graph going through each particular one, if we cannot find any of the pairs, or if the pairs are at the bottom, we would just keep on branching out for every particular node. So that means that when we look at our time complexity, this would be O of n for iterating over n pairs to build the adjacency list, plus O of n times n in the worst case when we do our depth first search. So this would reduce down to O of n squared.
Yep, and the space complexity?
For the space complexity, our adjacency list, due to the number of pairs we have being n, I believe the space complexity would simply be O of n, simply because what's dominating our space complexity is our adjacency list that we've constructed.
Okay.
And because we have n parents, that means we have O of n in terms of our size.
Okay, so thanks for that. So now we can jump to the next one. So this time I want you to write a function that takes in the pairs and one of the individuals as input. And I want you to return that individual's earliest known ancestor. So that would be the ancestor that's the farthest distance away. So if you look in line 25, you'll see for the output for the third test case, if you're given 6 as the input, we'll return 14, because if you look on line 12, you see that 6 has ancestors 3, 5, 2, 4, and 14. So because 14 is the earliest, that's the one we return. But on line 27, 14 has no ancestors, hence we'll return null or -1. So we have 2 different graphs because of just 2 different sets of test cases. So you can take some time again and read through the problem some more. Then you can let me know your approach, and then you can get started coding.
So okay. So I think it's I can use the similar approach in question 2 because it's just like I can do BFS from the given node and do and what I need to do is to return the return the last level, one of the last level node of the in the BFS process. Yeah.
Okay, yeah, that sounds like a good approach. So you can get started when you're ready.
Okay. Yeah, I think the test passed.
Yeah, so 4, 14, and 1, that looks good. So what's the time complexity resolution?
It's ON because like the building hash map takes ON, and for the BFS also takes ON because I will visit no more than all the nodes for once because it's a directed a graph. And space complexity is also ON because hash map takes ON, and my queue used to like traverse used to do the BFS is also takes ON, and the level array it's also ON.
Okay, so thanks for going through all those questions for me. So that's all.
Okay, and so what if 4 has 2 ancestors coming out of here? Would I return both as the furthest ancestor?
Any one of them.
Any one of them? Okay, cool. So I think I can reuse some code that I wrote before.
Okay.
Yeah. So first, child key map is still important, but now we're only working with one input. So this will just be node. I'll keep it at node 1 just for the sake of reusing my code. All of this down here would be unnecessary. I'm going to delete this as well. Okay. So I'm going to keep going until branches becomes null. And when branches becomes null, that means the previous level on the tree would be the highest ancestor. So if new branches.
So I guess before you write the code, could you walk me through how your approach is going to
Oh
work?
yeah. So I'm going to reuse this code to identify since it goes in layers. So say we start with 6, branches will go from 6 to 3, 5 to 1, 2, 4, and then to 14. And then after that, new branches in my code down here would be null because 14 has no parents. And I basically want to take the branch level of branches right before it becomes null, and this while statement finally pings. And I'll grab any of the parents, any of the nodes at that final level to be the highest ancestor. And I still have to kind of think about how I would do the case where you're given the top level one where it should be -1. But yeah.
But I'm not sure I fully understand. So how do you find the individual with the earliest ancestor?
So the way I work up the tree here, like every single time we have branches. So branches starts at 6, and then on the next iteration of the while loop, it will be 3 and 5, and essentially you keep working your way up the tree until branches becomes null. So like once you reach this point, branches will become null in the next iteration because there are no more ancestors to take account of. And branches before it becomes null, that level of branches will be the highest ancestor of your original node. So I want to basically save the state of branches right before it gets null because that'll be the highest level of the tree that has ancestors related to the given node.
What if you're looking at 9 and 14 gets to null before you get to 15?
Well, because of the way I'm building it, so 14 will be null, but so yeah, we start at 9, right?
Yeah.
So 9 branch will be 4 and 12, and then we'll go to 4 and 13. Then because of the try except logic that I have here, the parent of 14. The parent 14, it'll register that has no parents and it won't add anything to the ancestors, but 13 will have an ancestor. So the parent of 13 will still get appended to new branches. So even though this doesn't have a parent, new branches still won't be null, and it'll know that there's still one more passage.
Okay, that sounds like a good approach. So you can get started when you're ready.
Okay, so we have 14, 14, 14, 2.
So what's the time complexity solution?
Okay, this is the last question.
Yeah.
Okay, so I'm gonna wipe what I have from before and try to think about it again from scratch. So for time complexity, I would still call this one order of n time because it's steps ordered in a pair.
Okay. And space complexity?
Yes, and then so for branches, yeah, I guess this one I'm still kind of unsure about. So, or actually no, for time complexity is fine. For time complexity it is log n because it's just going to step through. It's going to step up the tree, and the height of the tree is log n, so that's fine. And yeah, so same complexity as before, n plus log n, which is order of n.
Okay, and the space complexity?
Yes, and then okay, space complexity. As I did before, it's to be O of n space, since you're essentially just storing all the pairs again, but in another format. And then for this second one, yeah. So any given branch. Yeah, I'm tempted to say log n space again because I'm unsure what the maximum, I guess, like. So this is kind of like a flipped binary tree where since each child can have at max 2 parents, you can essentially flip the whole graph and it would satisfy a binary tree. So what's the number of leaves of a binary tree given the number of nodes? So that would be the order of the space, but I'm not too sure what that is. I think I'm gonna continue running with calling it O of log n space. And then for ancestors, yeah, so worst case scenario, we store the whole tree, which is order of n again. So then we have order of 2n plus log n space, which would simplify to order of n space.
Okay.
Space.
So thanks for going through.
Quick question. For this particular set of examples here, is this the same as this graph here, or are they different?
Yeah, it's the same. There's 2 different graphs, so 2 different test cases. Pairs 1, pairs 2. Yeah, that's for the first one.
Okay. So for this first one, where is 1 actually? Oh, it's pairs 1. Sorry.
Yeah.
Let's see. Okay. Okay. So here's my idea. I think we can actually adapt the code that I previously wrote for the prior question. And one addition we can add to make this question possible is a new variable that we call depth. So for each particular run in our recursion, we keep track of the depth. And if we find that particular ancestor when we're scanning through all those particular, let me rephrase that actually. So you know how in our previous iteration, we looked at every node as a possible parent. When we find that particular ancestor, or when we find a particular child, we examine to see the depth of the node we were currently examining. And if that depth is larger than what the current depth is, we set the earliest ancestor to that new node we've just looked at.
Okay. And how do you keep track of the depth exactly?
When we perform recursion, whenever we do 4 neighbors in adjacent list of node, we can increase the depth counter by 1, such that in the recursive function, we're going to be passing in depth plus 1 each time we call it.
Okay, that sounds like a good approach. So you can get started when you're ready.
I mean, a bit of a frantic rush, if you understand.
Yeah, for sure. What you have looks good. So what's the time complexity for solution?
So I think this is still the same here where we have O of n when we're iterating over our n pairs. In this scenario, the worst case is iterating over all n nodes, and we have O of n for all of our individuals here. So I think this would be the same as our last scenario, where this would be O of n squared, simply because we iterate over all n individuals, and then when we iterate over the tree, the worst case is O of n, so O of n squared.
Okay, and the space complexity?
We know that our result, as well as our max depth that we've added this time around, are simply constants, so we don't add to our total space complexity. So I think it would still be O of n, simply because the main constraint of our space complexity has to deal with the adjacency list.
Okay, so thanks for going through all the problems with me. That's all I had.